Okay. By the end of this lesson, you'll be able to understand the relationship between intensity and number of sources, what happens to the intensity when volume is doubled, explain what logarithms do, how to convert between intensity and decibels, and what happens to decibels when volume is doubled. Here we go. Based upon the pre-quiz, actually, you can just look at the equation first. Figure it out. Neighbor, what do you think?
112. Oh. But is it like 3 times 24? So it's like 4?
I like to have a myself.
No, it's
Yeah.
like 3 times 3 and 4.
The correct answer is E. 1/9. The radius is squared. Yes? My hope is that you'll be able to rock your socks off of every problem like that. Like, you've seen that throughout the entire year. Power.
Power.
All right. Visualize this for me. Still pond. I throw a rock in it. The ripples go out in concentric circles. Yes? If you have a Bluetooth speaker in the middle of the room, it's creating sound waves that are concentric spheres. Can you visualize that?
Yeah.
Okay.
Bigger they are, they're different than a wall.
So what intensity communicates is how much energy there is per area. Okay. Here's my analogy. You have a jar of peanut butter. Get a spoonful. If you eat it straight out, that's like you're like at the speaker. Okay. Peanut butter represents how much energy. Okay. If I take a step away, that's like taking that spoonful of peanut butter and spreading over a saltine cracker. Okay. Same amount of energy is spread out a little bit. If I take that same spoonful of peanut butter, and I take another step away. That's like taking that same spoon of peanut butter and spreading it over a piece of bread. Same amount of energy just spread over a bigger area. If I take another step away, same spoonful of peanut butter spread out over a pizza crust. That energy is getting more and more diluted, it's more and more spread out. That's why it's harder to hear someone when they're further away. It's the same amount of energy, it's just being spread out over and over a greater area. All right with that? Okay. So that's what intensity communicates, how much energy there is for a given amount of area.
So if you look at form of intensity, you probably will have the eardrum to which way turn to dust.
Maybe.
Or blow up.
Okay? Try that one. Have a conversation.
The test is next week. Next week? Okay, because I want to say next Wednesday. So first
Like, is this the same as volleyball?
Good question.
Oh, okay.
Okay, correct answer is. Correct answer is C. Okay. Okay. This is an important relationship. The number of sources and your intensity go hand in hand. It is a linear relationship. Okay. This is intuitive. If you have one source has an intensity of 400, then three sources is going to be 400 plus 400 plus 400, be 1200. Those two go hand in hand. You good at that? Okay. This makes sense to us mathematically. This is a comfort zone. So number of sources and intensity, put that in your brain like, okay, those are good, these are good, okay? The intuition stops after this. Okay? The relationships are not linear. Okay, but intensity and number of sources go hand in hand. Okay? Try that one. Tell your neighbor.
Oh, let's see. No, exactly. I just didn't see it. I just didn't.
Correct answer is? C. Correct answer is C. Okay. If we hear something that we would describe as twice as loud, like, oh, that's twice as loud. If we go and measure that the intensity, we find out that it's not twice the intensity, but 10 times the intensity. Why? I don't know. That's just how we're wired. It's biology. Okay? I'm just here communicating. Here's what we would describe as twice as loud, and when we go to measure it, it's 10 times the intensity. Okay?
You synchronize, which is extremely hard.
Tell your neighbor what you think. Correct answer is. Correct answer is C. Because intensity and number of sources go hand in hand. To get the double the perceived volume, you need 10 times the intensity. You also need 10 times the number of sources. Intensity and number of sources go hand in hand. Okay? All right with that? All right. So this is going to be more or less proof of concept. Google or like pull up a YouTube that is, we'll say, 200 hertz. Like on a video, a lot of them have like a light blue screen. I need people pulling out your phones. Pull up a video. Few hundred hertz. Few hundred hertz. Tone like test. It's like a light blue screen is the thumbnail. Play it. Get past the ads.
Want to break from the ad?
Once it
Want it on full volume?
yeah, full volume. 200 hertz.
Oh God.
Test tone. Once it's working, go ahead and press pause.
This is just getting weird. I just need a visual on the formula. That's all.
You're gonna try past the license about
Yeah, play it. Get past the ads. Full volume. Then press pause. We're getting all our everything ready. Okay. Now, go ahead and press pause. Raise your hand if you have it queued, ready to go. Okay. Okay. We'll get you guys here momentarily. Okay. I recognize this demonstration has lots of faults. Our volumes aren't the same. Max volumes aren't, like everybody put it in max volumes. Our phones are different. Yes. We're different distances away. Yes. We're just going to get a ballpark here. Okay. David's going to play his. And then the rest of the 10 are going to play theirs. Ready? Go. We would say, oh, that's twice as loud. Good with that. Pause.
You need
Okay.
to synchronize.
Try this. Do this question. Got your neighbor?
Yeah.
Well, you need 10 the first time, and then you need 10 again.
So maybe.
Okay. Correct answer is? Correct answer is D. Okay. Shiv and Luke, play your tone. Play the 200. Go. Okay. Everybody else. Ready? Play. We would say that's roughly twice as loud. Went from 2 to 20-ish. Pause. Okay? Good with that? All right. If we double the perceived volume, that is 10 times the intensity, 10 times the number of sources. Because intensity and number of sources go hand in hand. Correct answer is A. Everybody good? Okay. To have the volume, you divide by 10 for number of sources and intensity. Okay. All right. So the fact that we are multiplying and dividing by 10 screams logarithms. Okay. Now, I don't know your personal experience in math class, but here was mine in high school. I rocked the socks off of this test. Okay. Why? Because I could memorize this. Like the B gets big, the Y goes the other side, and the X gets small. And I put that on the top of my test, and I knew how to manipulate my calculator to give me the answer. I aced that thing. I'm like, boom, easy. I'm such a genius. But I had no idea what I was doing. Like I didn't have a comprehension of what log. I just knew how to do the pattern. Okay. I think Harrison does a better job at teaching what logarithms do. But just in case you fell through the cracks, I want you to bring some conceptual understanding of what this is. Okay. So, if you have 100, that is equal to 10 to the what? 10 to the second power. Good with that? In this class, we're always just going to deal with base 10. Okay. If I hit in your calculator 100 log, it's going to spit out, it's going to display what on the calculator? 2. Okay. If I have 10,000, that's 10 to the what? 4. If I say log of 10,000, my calculator is going to read what? 4. When we hit the log of some number, what is it focusing on? What is it communicating? When we press the log, what is it describing? Okay, how many zeros there are is one way to describe it. It would be what power, what exponent is 10 raised to 2. That's the whole point, is to focus on the exponent. It's exponential growth. Heard of those type of phrases? That's because it's focusing on that. Okay? If I give you 5,000, if I say log of 5,000, I'm not asking that you know the answer to that without using a calculator. But I want you to estimate, figure out what is the range that log of 5,000, what two numbers could that be between? Think about it. What's the range that could be? It's going to be between this number and this number. Tell your neighbor and tell them why it's going to be between those two numbers. All right, it's going to be between which two numbers? 3 and 4. It's got to be between those two numbers because 10 to the third is equal to 1,000. 10 to the fourth is 10,000. So 5,000 lies between these two numbers. To actually figure out the answer, it's not intuitive. It is not 3.5. Okay? Because a logarithmic scale is not linear. It is not intuitive. You must use a calculator to get, if you're not given these easy type of questions. Does that make sense? Okay. Now, a Richter scale is an example of a logarithmic scale. Tokyo gets hit by an earthquake that has a Richter scale, like has an earthquake of, let's say, 5 on the Richter scale. And then the next day gets hit with an earthquake of 7 on the Richter scale. Okay? And we're thinking, oh, it's just 2 more. No. That is saying 5 on the Richter scale, and then going 7 on the Richter scale. That is 100 times more intense. The intensity was 100 times more. That's a substantial amount. You okay with that? Decibels has the same pattern. Okay, so we use logs. So there are 4 blaring car horns produce a total sound of 70 decibels. What is the intensity of this sound?
So if it's 2 to 3, it's literally squared.
Okay, so I'm going to use this equation. Okay. My I naught, or I sub O, this is threshold of hearing. This is the quietest volume that we can hear. The quietest intensity that we can hear. So to figure out this intensity, put it in that equation. And I'm going to solve for I. So bringing that over. To get log the other side, you can either apply what you've learned in math class, or you can use your calculator. You've got a log button. To do inverse log, you hit second and hit the log button, which above your log button is going to be printed 10 to the x, because that's the inverse of log. So you end up with 10 to the 7th power is equal to I over 1 times 10 to the negative 12. Everybody okay with that? Okay. This is the same thing as 1 times 10 to the 7th. Just put it in scientific notation. Bringing this over here, you can either do it on your calculator or do it in your head, because, hey, you're just adding exponents. You end up with 1 times 10 to the negative 5th watts per meter squared. Is the intensity of 1 car horn, or sorry, 4 car horn blaring.
Where do you get the 10 to the negative 12?
Just a factoid. It's a constant. It's for human hearing. It's the lowest intensity that we can hear.
What's the highest intensity we can hear before our brains get turned into mist?
Good question.
219.
So the threshold of pain.
No, the threshold that anything can exist in.
You know what? Don't know.
The loudest sound we have recorded in the universe is 2 black holes colliding. And based on how it was sounded, it sounded like water.
Okay, so how are we doing with that? Good? Here. What? Watts per meter squared. So power over area. Good? Okay, so follow-up question. This is the intensity of four car horns. What would be the intensity of one car horn? Tell your neighbor. How'd you find the intensity of one car horn if you know the intensity of four car horns? Okay. Intensity and number of sources go hand in hand. So if this is four car horns, one car horn would just be a fourth of that. You okay with that? Those two go together. So the intensity of one car horn, I know I'm not writing this in correct scientific notation, just trying to teach here. That would be one car horn, a fourth of what we had for four car horns. You right with that? That makes sense. Now, how many decibels is that? I want you to just estimate four car horns with 70 decibels. How many decibels do you think it's going to be for one car horn? Whatever you think, it's probably going to be wrong because decibels are not intuitive. You have to use the equation. That's kind of the point. Okay, so we're looking for our decibels. All right, 10 times log of 0.25 times 10 to the negative fifth over 1 times 10 to the negative 12th. Do that in your calculator. When you do log of this, you end up with 6.4. So your answer is 64 decibels. It isn't. That is not intuitive at all. Four car horns, 70 decibels. A one car horn, 64. You've got to do the math. There's not a pattern that, unless you've practiced with that, where you're going to see it's not intuitive. It's not a linear relationship. You got to do the math. You okay with that? Okay. Questions there? All right, so one car horn is 64 decibels. If we doubled the perceived volume, how many decibels would that be? Tell your neighbor.
Sure.
Same thing, but building books and food for the
Yeah, it's also
it's only one color.
Yeah.
But like building has the same but
yeah.
yeah, right?
Correct answer is. Correct answer is A. Okay, this is the other factoid. If we double the perceived volume, we add 10 to our decibels. We multiply by 10 by the intensity and number of sources. Okay? Now, real quick, if that doesn't mesh with your understanding of how logarithms work, I'm going to take a little deep dive that is not necessary for your understanding, but it'll help remove that little mental splinter if that's bugging you. If you don't have a mental splinter in your brain right now, just ignore this. Okay. Technically, the 6.4, this is the logarithmic scale. Okay. This would be how many bells, like Alexander Graham Bell. For reasons that someone decided that decibels is a better way to describe that, a decimeter is a tenth of a meter. A decibel is a tenth of a bell.
What?
So if we got rid of this 10 in this equation, this would be how many bells. So when we add 1, that would be multiplying by 10. But we like it decibels, and so we describe it, we multiply that to convert it from bells to decibels. So this is your actual logarithmic scale. If that made no sense, just let that roll on by. Doesn't matter at all. Okay? So we do with decibels. Try that one out. Wait for it. Do it in your brain. Your neighbor?
What?
Yeah, I
don't.
Correct answer is D. Correct answer is D. Dangerous dinosaurs. You multiply your intensity and number of resources by 10, you add 10 to your decibels. Okay? Then you double the perceived volume. Okay? You can only do that pattern if I say you double the perceived volume. If you don't have that pattern, you have to do the math. Okay? Your neighbor. Your thoughts.
B.
Why do you think so?
I mean,
That's not.
according.
I don't know what this. How much did you get it? What? I didn't say fail.
Bro, I
Like
don't.
20 and then. Yeah.
Dude,
by
if
10.
it's 2x, so you subtract.
What? I need to put it.
If it's minus, then that's fine.
Oh,
Because you
Oh,
add 10, if you add 10 times 2.
I was
Yeah.
how does that work?
Okay, that makes sense.
Times 10 is.
Do you have any advice?
That's my definitely. That's my definitely.
There was one thing about
You're right. Correct answer is
A.
What?
going from 95 decibels to 85 decibels. We subtracted 10. And therefore, we do what to the number of sources, or sorry, to our intensity?
Yeah.
We divide by 10. Yes? That makes sense? We subtract 10 decibels, we divide by 10 for intensity. Going from 85 to 75, we subtract 10, so we divide by 10 again. Correct answer is C.
So we can multiply by intensity, but addition.
How are we doing with that? Okay, you see the pattern. Intensity number of sources, multiply by 10 if doubled. For decibels, you add 10 if doubled.
Add 10 it doubles.
The perceived volume. Yep.
So all you do.
Okay. All right. What this chart is showing. Here's our threshold of hearing. 0 decibels times 10 to the negative 12 intensity. Every time we go up a row, we are doubling the perceived volume. It's twice as loud as the row below that. We add 10 to our decibels. We multiply by 10 to the intensity. Okay? And the examples of that, I'm not really take it or leave it.
So add 10 to decibels. The decibels is volume, correct?
Ten more.
It's one way to communicate that.
Okay, so it technically is.
So Vincent, the thing that I'm concerned about, if I say double the perceived volume, I don't want you to double your decibels. That's why my hesitancy.
I'm not intending on doing that.
Everybody good there?
Yes, that's like multiplication.
Okay. So the range of hearing for human. This down here. So this, the x-axis is frequency. So like high pitch. Okay. The y-axis is volume. Okay. Threshold of hearing. We hear higher pitched things quieter than we hear lower pitched things. Okay. So, and then this is like threshold of pain. Like this is causing damage. We are all aware that loud noises aren't good for our hearing, or is not good for our hearing. Okay. But here, this was when I found this out. I was like, "What?" Not only is it a function of volume, but it's also a function of how long you're exposed to that noise. Okay. For example, lawnmowers, they aren't inherently loud, but if you are exposed to that for a long period of time, which everybody is when you mow your lawn, you're causing hearing damage. So, like, wear protective hearing things. Okay. So that's why, like headphones, AirPods, they give you like, hey, don't go over 85 decibels, because if you expose yourself for 8 hours, that's causing hearing damage. 85 isn't that loud. You're like, that's not loud. Okay. Gotta feel the music. Like, you gotta, like, if you want to go into a career path that's going to have a prospective job market, audiology is a pretty good one based upon how loud you guys listen to your music. Okay. So I just found people are like, hey, what about other things? So, like, humans, our range of hearing is 20 to 20,000. Dogs are from 15 hertz to 50,000 hertz. Cats are a little higher. Dolphins are like crazy. Cool with that? And that's just like some examples. So, you got a worksheet and a lab quiz on Thursday. Okay? So, there you go. Yeah.
Next ones are they two in this?
It is